I'm Mariel Alquisira, and today I'll be presenting the results I obtained from evidence 2. First, a discrete time state-space model is represented by a z-domain from inputs and outputs in state variables first-order equation. It can be used to analyze the stability and transient response of a system. On the other hand, a continuous state-space model is represented in an S-domain differential equation. In continuous time, it is often easier to define a parameterized state-space model because physical laws are often described in differential equations. Almost every continuous time can be written in discrete time. However, many discrete times aren't continuous time processes. Both transfer functions are the impulse responses of the systems in their respective domain. In the continuous images, it can be closely observed the difference between continuous and discrete. We can conclude from the images that continuous is an analog plane while discrete is a digital domain, respectively S-plane and Z-plane. Furthermore, their state-space equations show it can be observed the A, B, C matrix, and the output equation of C for the continuous time. You can estimate the continuous state-space model using both times and frequency domain data. When transferring from continuous time to discrete time, information can be lost between samples. This is known as discretenation. In discrete systems, add delay to your systems that decreases the bandwidth. Another difference is pole stability. As in continuous time, they are placed on the left-hand side, while in discrete systems, the stability part region is inside the unit circle. Pole placement is important, and the respective pole locations, equations as well. Now, in procedure to design a state feedback controller with observer, first we focus on discrete state-space model, and given the measurements of the state vector xk, and obtain a linear state feedback. Afterward, we should determine whether the system is controllable, so we can move forward and in order to do whatever the given dynamic system under the control input. Next is the characteristic equation. We place our desired placement on the closed loop poles, P1, P2, so on, Pn. It's in the next slide. And they are the roots of the desired characteristic polynomial. With its determinant, the eigenvalues help us understand the placement of the poles. Utilizing the same characteristic polynomial, a second pole placement is stated with this equation, and it is its new placement of the desired closed loop poles. Then, the gain vector L helps us move the poles as needed in the characteristic polynomial. And finally, the reference input gain is to know the ratio of the steady-state output of a system and its constant input. Now, an observer is designed to estimate the state of the system. This is related to state feedback since we can't always measure the system state, and therefore we design an observer to estimate it and help apply our feedback, an estimate of what we believe would be the estimate of the state. So in summary, an observer is designed to estimate the state of the system. Now, moving on with the Matlab functions and state feedback design, the function SS here generates the state space model of the polynomial model from evidence 1, as we can see here. The function next is CTRB, which is the controllability. And it is very important because it indicates the controllability of the system. As we mentioned earlier, a system has to be controllable and observable. That checks out in our system. And there exist control signals which allows the system to reach any state of the finite time. And so here we have the discrete function and we have the continuous, which can be visualized in the screen, and the Matlab function. Moving on, we have the state feedback gain and the observer gain, which are important because this tells us the pole location in discrete time for both of the poles, the ones that we have and the one that we want to have. And finally, we have the Bode diagram, which obtains the frequency response from the Bode diagram, and we're able to understand better the model. And we have grid on, which allows us to see better. And in overall, this helps a lot with the analyzing. And now moving on to the closed loop poles of discrete time systems, it is important to know that if the system is controllable, then the user can freely place closed loop poles even if they are not the best option. However, if this is not the case, we have to take into consideration the desired speed, desired damping, poles, and zeros of the plant. And now moving on to my selection of the closed loop poles. I chose a 6-order system and verified my system was observable because in order for a closed loop system to be stable, all poles from the z-plane must lay inside the unit circle. And the more poles inside, the more marginally stable this can be. My pole choice is shown from the code and the pole 0 map, providing my system is stable. And as I mentioned earlier, the pole should be within the limits of each unit circle. So this is my system. Now moving on, the bandwidth taken from the Bode plot is 0.2 rads per second, and there is no resonance peak. So this is a good indicator that we did choose a good model. And moving on, the settling time, as you can picture here, is 30 seconds, which has a good movement. And finally, the trolley force, which in my opinion was the most challenging for me, is under the requirements and it does not exceed the 40 kilonewtons. Although this system can be improved in the future as we can take into consideration evidence 1 and find ways to improve this and make it the trolley force a lot smoother than it currently is. So in conclusion, I really enjoyed this class. It was really challenging for me. Although it was challenging, it did help me grow a lot and I better understood Matlab, Simulink, and through the assignments, I was able to apply my concepts of control and it was a very rewarding process. Thank you.